Hello, everybody. This is Bert Dixon, presenting today on the convergence of the Taylor series and a Maclaurin series as well. So in the last lesson, we saw this table, which I'll pull up here. We saw this table of common and useful Maclaurin series, and we said, for example, cosine, this Maclaurin series for cosine works for all values of x, which is incredibly powerful because that means we can use this series for cosine no matter what x value we're using. Whereas some of the series are a little bit more restrictive. This series only converges when x is between -1 and 1. This one only converges when x is between -1 and 1, and so on. So some of them you see work for all real numbers, whereas others are restricted. And so when we looked at this table last week, we just looked at the series. We didn't really pay attention to the intervals. These are the intervals of convergence, just like you found in the last section on your own. And so that's what we're going to look for, is we're going to look at proving some of these things by finding the interval of convergence for the Maclaurin series that we have. And so to show that that sine converges for all real values of x, note that, remember, sine is the odd powers. So we have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. And that is the sum from n equals 0 to infinity of -1 to the n. That creates the alternating signs. And x to the 2n plus 1 creates odd powers of x. And then we're dividing that by an odd number, the same odd number, 2n plus 1. And so to find the interval of convergence, to find the interval of convergence for this series, we'll do the same thing we did in many of the problems from 10.7, and that is we'll use the ratio test. So we'll start off with L equals the limit as n approaches infinity of x to the 2n plus 3 over 2n plus 3 factorial divided by x to the 2n plus 1 over 2n plus 1 factorial. You'll notice that I left off the -1 to the n component because we're taking the absolute value, so we don't really care if this turns out to be positive or negative. When we take the absolute value, it's going to be positive anyway. So then evaluating this limit, we have x to the 2n plus 3 over x to the 2n plus 1 times 2n plus 1 factorial over 2n plus 3 factorial. And if we simplify that, that is the limit as n approaches infinity. The 3 is two units higher than the 1, and so that means we have x squared, because the difference of those powers is 2. And then if we simplify the factorials, we would end up with 2n plus 3 times 2n plus 2, the last two numbers, because since this number is 2 units bigger, that's like doing 3 factorial over 5 factorial. 3 times 2 times 1, and 5 times 4 times 3 times 2 times 1. So we see those all cancel with those, leaving the two biggest numbers. So that's what I have here, is the two biggest numbers. And remember, x isn't changing, x is a constant, but n is approaching infinity. So this limit is going to be 0 no matter what x is. And 0 is less than 1. So this series passes the ratio test no matter what x is. And so we can say this series converges for x in between -infinity and infinity. Okay, so I'd like you to go ahead and try part B. Do do this, the problem is very similar to the one we just did. So if you use the ratio test to do this one, first thing you want to do is recall what is the cosine Maclaurin series. Write that down, and then try to write it in sigma notation like I did here, and then see if you can find the interval of convergence. So cosine is the even powers in the alternating series, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. And so in sigma notation, that is, again, negative 1 to the n because it's an alternating series, x to the 2n over 2n factorial. And so if we set up the ratio test, L is going to be the limit as n approaches infinity of x to the 2n plus 2 over 2n plus 2 factorial divided by x to the 2n over 2n factorial. And that is the limit as n approaches infinity, x to the 2n plus 2 over x to the 2n, and then 2n factorial over 2n plus 2 factorial. And just like we saw in the previous example, this limit is, if we simplify this expression, that's just x squared, because the power in the top is 2 greater than it is in the bottom. And this expression just becomes 1 over 2n plus 2 times 2n plus 1. So the two biggest numbers left in the bottom that don't cancel. And so we have the limit as n approaches infinity of x squared over 2n plus 2 times 2n plus 1. And as n goes to infinity, this limit again is 0 for all x. So this series converges. Since this is less than 1, this series converges for all real x. That is, x is in between negative infinity and infinity. Okay, and we'll go ahead and do the find the radius of convergence, or the interval of convergence, for inverse tangent. This one is not all real numbers, so my directions don't really apply to C because this one isn't all real numbers, but we'll see why. If we write out this series, it is x minus x cubed over 3, not factorial, just 3, plus x to the 5th over 5, and so on. That is negative 1 to the n, x to the 2n plus 1 over 2n plus 1. So we can write that as a sum, as n goes from 0 to infinity, of negative 1 to the n, x to the 2n plus 1 over 2n plus 1. And so if we set this up with the ratio test, L equals the limit as n approaches infinity. In the top, we're going to have x to the 2n plus 3 over 2n plus 3 divided by x to the 2n plus 1 over 2n plus 1. And simplifying, we get x to the 2n plus 3 over x to the 2n plus 1, and 2n plus 1 over 2n plus 3. So this, as n approaches infinity, this approaches 1 because it's really just 2n over 2n, which approaches, sorry, I wrote 0 and I said 1. It approaches 1, and this is equal to x squared. And so we're just going to have x squared. And so L is equal to x squared. And so this will converge when x squared is less than 1, which means x has to be in between -1 and 1. And so that gives us the open interval where it converges. Now we just need to test the endpoints. And so when we test x equals -1, it becomes the sum from n equals 0 to infinity of -1 to the n. Let's see, -1 to the 2n plus 1, that's an odd power. So an odd power is always going to be -1, and then this in the denominator is going to be 2n plus 1. And so this is still an alternating series. We just have -1 to the n plus 1 over 2n plus 1. So it's still an alternating series. The reason why it's n plus 1 is because I just added the exponents here to get n plus 1. And so that creates an alternating series. So this converges by the alternating series test. Since the limit as n approaches infinity of -1 to the n plus 1 over 2n plus 1 is equal to 0. So now if we look at the other endpoint, when x equals 1, we get -1 to the n, and then -1 to an, this is now +1 to an odd power is just going to be 1. And so this again is an alternating series. And it converges by the alternating series test. So the interval of convergence, or we can say so the series converges for x in between and including both endpoints. So from -1 to 1 inclusive of the endpoints. And again, we can go back to that table and see that that's exactly what it says here for inverse tangent. Okay, next we're going to look at the remainder estimation theorem, which says if we have a Maclaurin series or a Taylor series, obviously if we let it go forever, then we have equality. So that's why if you look at, again, let's go back to the 10.8 notes. These are equal signs all the way down. It doesn't say approximately. It says this function is actually equal to this infinite series. But if we chop off this series, if we truncate it somewhere, let's say we chop it off right there, or chop this one off right there, then it becomes an approximation. And so we want to calculate how much error do we accumulate when we truncate the series that way. So when we chop it off, how much are we really losing? And so this theorem, the Lagrange error theorem, or which is also called the remainder estimation theorem, will help us determine how much error we're going to accumulate when we truncate a Taylor or a Maclaurin series. Okay, and so we will know what A is, we will know what N is. The only thing that we have to calculate is M, and that is very similar to what we did with the error theorem for the trapezoidal rule and Simpson's rule. We have to calculate the maximum magnitude. So this is the M equals the maximum magnitude of the n+1 derivative at some point C, where C is on the interval from A to X or X to A, depending on which one is bigger, A or the X value that we're currently plugging in. Okay, and so when we say magnitude, that means we don't care what the sign is. It can be a positive number or a negative number. We're just looking for the maximum absolute value. So if it helps you to put absolute value around that, we're trying to find the maximum value of this absolute value of the n+1 derivative of the function. So that may be a little bit confusing looking at the theorem, so let's actually try it out. And so for this series, we have this looks like the series for e to the x, and so e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, x to the 4th over 4 factorial, going on forever and ever and ever. So that we get equality when we let it go forever. But if we chop it off after the third degree term, we're truncating it. And so we're saying now e to the x is approximately p sub 3 of x, which is 1 plus x cubed, x squared over 2 factorial plus x cubed over 3 factorial. Okay, so we have let it go to n equals 3. So we see that in two places. N equals 3, we see that here. We see that here. Third power, third factorial. Okay, and so using the remainder estimation theorem or the Lagrange error form, we see that our error is less than or equal to m x minus 0. A is 0 because this is a Maclaurin series. Maclaurin is always a equals 0. And so since n is 3, then this is going to be the 4th power. It's one higher, according to the theorem here, n plus 1. And then in the denominator, it's going to be n plus 1 factorial, so that's going to be 4 factorial. Okay, and so now we need to figure out what m is. And so we need the 4th derivative of e to the x. So f of x equals e to the x. The first derivative is e to the x. The second derivative is e to the x. The third derivative is e to the x. And the fourth derivative is e to the x. So that's what we need, is the 4th derivative. So we want to find out what is the maximum value of e to the c, where c is in between, it says x is between negative 0.5 and positive 0.5, and a is 0. So c basically can be anything in between negative 0.5 and positive 0.5. Okay, and so the value that will make this as large as possible, in this case, is the right endpoint. And so m is going to be e to the 0.5, and that is about 1.6487. And so we can say our error is less than 1.6487. The biggest x value that we can plug in is 0.5 to the fourth, according to this again, and then divided by 4 factorial. So now if you go ahead and type that into your calculator, we'll see that that is, our error is smaller than 0.00429. So by truncating this series after the third degree term, we know that our error is going to be smaller than 1/100th for sure. It's as it says here, it's definitely less than 0.00429. In our next example, we see that this is a Taylor series, and it is a Taylor series for cosine, but it's not a Maclaurin series. It's a Taylor series where a is pi over 4. We can see that because of the x minus pi over 4 and x minus pi over 4 squared and so on. So we can see that a is equal to pi over 4 and x is equal to 2 because that's the value that we're plugging in to the cosine function. Okay, so please pause your video, try this one out, and then press play when you're ready to see the solution. So for this one, we can say our error is less than or equal to m, the absolute value of m. It's x minus a, so that's going to be 2 minus pi over 4. Let's see, this goes to the second power, and so n is equal to 2, which means this goes to 1 power higher, so third power over 3 factorial. And so now we need to calculate m. So if f of x is cosine x, f prime of x is negative sine x, f double prime of x is negative cosine x, and f triple prime of x is sine x. And so m is the maximum magnitude of this cosine graph, or sorry, this sine graph. Sine, remember sine looks like this, and this is pi reaches its high point at pi over 2, and so on. And so the maximum magnitude that we're going to get from this is 1, and that's where, so the third derivative at c is equal to sine of c, where c is on the interval, c is anything between, let's see, x and a, so between 2 and pi over 4, pi over 4 to 2, and pi over 2 is in between there. 2 would be right about here, and pi over 4 is obviously over here, so the high point in between those is definitely 1. So this took a little bit of an analysis in the graph to realize that our m value here is 1. But in the future, whenever your function is a sine or a cosine value, it's customary to just say m equals 1, because we know no matter how many derivatives we take of sine or cosine, we're going to end up with another sine or cosine. And sine and cosine are never any bigger than 1. And so it's generally, whenever you see that you're dealing with a sine or a cosine function, just skip all of this and just go right to m equals 1. And so we're going to have 1, 2 minus pi over 4 to the third power over 3 factorial. And that is about 2.986. So our error for this one is quite a bit bigger than our error for the last problem. We do have a pretty significant error if we only use the first 3 terms of this series. And so it would be a good idea, if you wanted more accuracy, to expand this and use more terms in your series. All right, and then example 4. This time we're going to see for what values of x can we use this series and get an error smaller than we want. So this time we know the error is 0.0005, or we want our error to be less than that. And so, or we want to keep our error smaller than that. Okay, so our error estimation theorem, we would have the error is less than m. Let's see, this is Maclaurin, so it's going to be x minus 0. And now the question is, what is n? Now it looks like n equals 5, but notice that the next term in this would be minus x to the 7th over 7 factorial. So we could actually say that n equals 6, because if we stopped at n equals 6, n equals 6 and n equals 5 give us the same series, because if we fill in all the zeros, remember we had 0 plus x minus x, or plus 0 x squared over 2 factorial minus x cubed, when was it 2, over 3 factorial plus 0 x to the 4th over 4 factorial plus 0 or plus x to the 5th over 5 factorial plus 0 x to the 6th over 6 factorial, and then minus x to the 7th over 7 factorial. And so we could get this series by saying n is 5, but we could also say n is 6 because of the 0 term at the end. So if we have the option of using n equals 5 or n equals 6, we're better off calling it n equals 6, because then we get a smaller error estimation, which means we can then we'll get a larger interval of x values. So when you have an alternating series like this where we just have odd powers or even powers, you don't forget that the next term is 0, so you can include that. We can say we included the 0 term here. So it'd be stronger mathematically to say we included the 0x to the 6th over 6 factorial term, because now it looks like our series went longer. Okay, and so we're going to say n equals 6. And so this is now going to be to the 7th power over 7 factorial. And since this is a sine function, we're going to say m equals 1. And so now we have 1 x to the 7th over 7 factorial, and we want the absolute value of that to be less than 0.005. So we want this to be less than 0.0005. So that means we want x to the 7th over 7 factorial to be in between 0.0005 negative and 0.0005 positive. And so if we multiply by 7 factorial and then take the 7th root, okay, multiply by 7 factorial and take the 7th root. So I'll go ahead and do that on the calculator here. And so 0.0005 times 7 factorial is that number. and then we want to take the 7th root of that. So you can raise it to the 1/7 power. That's the easiest way to take a 7th root, is to raise it to the 1/7 power, and that gives us 1.141. So x, as long as we pick x values between negative 1.1411 and positive 1.1411, then we will have an error within 0.0005. So here are some good practice problems from section 10.9. I encourage you to go ahead and try those, and email me or visit me during office hours if you have questions on any of them.